There's a wide world of geometry nodes.
Shut the fuck up. You can only know what you can make if you know what tools you have in your workshop and what they're capable of. Similarly, you can only know what you can do with geometry nodes if you know what each node does. Unfortunately, there are about 275 nodes in Blender 4.3. Not so unfortunately, this video is about an hour long. This is the first nodes we are going to look at are called the input and output nodes. The first section in this is the constant nodes. Constant nodes are input nodes that provide fixed values such as numbers, colors, strings, or other data types to be used across a node tree. These are small, tiny nodes, so I'm just going to quickly roll over them. The first node is the Boolean node. This node gives a single Boolean value, either false or true. Next node in the list is the color node. This node basically allows you to choose a color. Moving on, we got the image node. This node lets you load an image file into the geometry node editor. Next up, we got the integer node. Like the name suggests, this node provides an integer value. Next is the material input node. This node gives you access to materials in the geometry node editor. Next is the rotation input node. This node allows you to control rotations. The string node lets you output a string value. The vector node basically creates a vector. The value node outputs a single numerical value. Coming up next, we got the collection node. This node allows you to input a collection into multiple sockets throughout the node tree. Last but not the least, object node. This allows you to input a singular object throughout the node tree. Before we move ahead, we should tackle some important concepts that help us better understand some of these nodes. The first of this concept is the concept of fields. While there's a very technical definition of what a field is, in Blender, in a practical sense, a field just means more than one value. So a node, when connected to a field, basically means it performs its operation on more than one value at once. How do you spot a field? If the node socket is a circle, it outputs a single value. If the node socket is a diamond, it outputs a field. If the node socket is a diamond with a circle inside, the node can output a field but is currently outputting a single value. Some nodes that output fields are the position node, index node, ID node, or the normal node. But there is a little more caveat to fields, because when I said a field is more than just one value, I lied. Now hang on with me for a second. A field is more than one value, but this value is not independent. It corresponds to a particular geometry element. What I mean by geometry elements is vertices, faces, edges, etc. So basically a field are a set of values that correspond to a specific geometry element. What are the values when I say fields give more than one value? Those values are called attributes. Attributes are basically data or information that correspond to a domain. For example, the position attribute in the point domain stores the position information, which is the data, of all the points, which is the domain, in a mesh. This makes geometry nodes more about data manipulation than anything else. How to view attributes? Attributes can be viewed using the spreadsheet editor. This window shows you the attributes of different domains. One important concept we need to understand is that the same kind of attribute can exist in multiple domains. For example, the position attribute we discussed earlier not only exists for the point domain, but also for the edge, face, spline, and whatever domain you can think of. How does a node determine which attribute of which domain should the node operate on? Well, that's where the tricky part comes in. This intuition a node has on which domain it should operate on is called field context. What is field context? Most nodes have some conditions associated with them. Like for example, take the set position node. This node's condition is that it operates on point domain by default. When you connect an input node like the position node to the set position node, since the position node is connected to the node which defaults to operating in the point domain, it is giving out position values of the point domain. This is the basis of field context. Input nodes like the position nodes and more nodes we'll discuss down the road bend to the context/conditions of the node ahead of it. One common misconception is that the node outputs the same data all the time. This is not true. For example, take this node setup. In the top part of the node tree, the position node outputs the position data in the point domain, whereas in the bottom part of the node tree, the position node outputs the position data in the face domain. Notice how the same position node outputs different data depending on the context of the nodes it is plugged into. That is the working of field context. Before we go ahead, I just want to take a few moments to talk about this project. This basically started out as nodes for myself to understand geometry nodes, and well, it has turned into this full-blown project where I'm explaining geometry nodes, and what I have discovered is that geometry nodes is insanely fucking detailed. The more I study it, the more I play with it, the more nuances I find with it, and hence I definitely cannot cover everything in this video, and that's why I made all my nodes that I used to study geometry nodes into an ebook. And also, I created another ebook called Nodal. This book contains a recipe style step by step explanation of 20 geometry node exercises that I went through that like changed and built my understanding of geometry nodes the most. This book will actually take you from 0 hours to 200 hours of experience in geometry nodes within the course of that book. And if you want to check out any of these stuff, they're on Gumroad and Blender Market. And I just want to say thank you for watching. This means a lot to me. So let's get on with the rest of the video. Next concept we'll be looking at is ID and group ID. Every geometry element is given a number starting from 0. This number is called its index. So for example, take this cube. This cube has 8 vertices and each one of this vertex has a number associated with it, and that's called its index. Index usually follows a particular order and therefore can be used as an identifier. But here lies the problem. Sometimes certain operations on the geometry can cause the geometry elements to be re-indexed, and hence index cannot be a reliable identifier. To counteract this problem, Blender has the ID attribute. This attribute can act as a unique identifier because it remains stable across operations. Group ID functions as a shared identifier used to divide geometry into distinct groups. This segmentation allows operations to target specific groups independently without affecting other groups. The next concept we are going to tackle is instances. Instead of actually duplicating the data, instancing reuses it, making the process more efficient. Instances can be nested, which means an instance can contain instances of different objects, and this can be done multiple times. This creates a hierarchy of instances. The top level instance is the topmost instance in the instance hierarchy. Nice, we have covered all the concepts required to understand geometry nodes. So let's just get on with it and finish the rest of the nodes. The next set of nodes are called scene data nodes. They allow for a dynamic interaction between scene elements and geometry nodes. The first of this set is the active camera node. This node outputs the scene's current active camera. Next is the collection info node. To access a collection in the geometry node editor, you can simply type its name in this text box, or you can simply drag a collection from the outliner into the geometry node editor. The node offers a separate children output, which outputs each object in the collection as a separate instance. The node also offers a reset children option, which removes all transforms from children when converting them to instances. The node offers two options for transform spaces, these being the original, which maintains the collection offset of the children, and the relative option, which joins the input collection into a single geometry while keeping their relative positions in the scene. Moving on, we got the object info node. This node retrieves data from selected objects from the outliner. Transform provides the object's transformation in matrix form. Location, rotation, and scale give information about the object's geometry. The as instance outputs the entire object as a single instance instead of realized geometry. The relative and the original transform options the node provides are similar to the collection info node discussed earlier. Next is the image info node. This node is used to retrieve data from images or videos. It takes in image and frame index as inputs and outputs the width and height of the image. The has alpha output gives a boolean indicating if the image has a transparency or not. The frame count gives the total number of frames in an image or a video sequence. FPS gives frames per second. Moving on, we got the is viewport node. This node outputs a true value when a set of geometry nodes is evaluated for the viewport and false for the final render. Up next, we got the scene time node. This node outputs the current time in the scene's animation in units of seconds or frames. The next set of nodes we are going to look at are called attribute nodes. The first of this set is the attribute statistic node. This node performs statistical operations such as mean, median, sum, finding the minimum or the maximum on a given attribute. The node also offers options for data type and domain selection. Next up, we have the domain size node. This node basically tells you how many points, edges, or faces, or any other geometric element are present in a given mesh. Next up is the blur attribute node. This node basically smoothens the attribute values. It takes in the attributes through the value input, and the iteration controls the number of times the attribute is smoothened. Weight acts like a factor of the smoothing effect. Next up is the capture attribute node. This node saves the result of a field onto the geometry and makes it available for other nodes. Instead of naming the stored attribute, it is accessed directly through the socket when connected to another node. The attributes saved by this node don't appear in the spreadsheet and are called anonymous attributes. Next up is the remove named attribute node. This node deletes a specific attribute with a certain name from the geometry. Removing unused attributes can improve performance and reduce memory usage. The last node in this set is the store named attribute node. This node saves the result of a field onto the geometry as an attribute with a specific name. It's like the capture attribute node, but instead you can give it a name. The next section is called the curve nodes. These allow you to parametrically control and generate curves in the geometry node editor. The first set of these nodes are called primitive nodes. These allow you to generate and control basic curve objects all through nodes. These nodes include the arc node, which generates a polyspline arc, the Bezier segment node, which generates a 2D Bezier spline from the given control points, the curve circle node, which generates a polyspline circle, the curve line node, which generates a polyspline line, the curve spiral node, which generates a polyspline in a spiral shape, the quadratic Bezier node, this generates a parabola type shape, the quadrilateral node, which generates a polygon from 4 points, and the star node, which generates a star-shaped polyspline. The next set of nodes we are going to cover are called output nodes. The first two nodes we're going to cover are the group input and output nodes. These are the first two nodes you see when you open the geometry node editor. The group input node gives you access to the node's group input sockets from the inside. These sockets act like external controls, letting you tweak stuff like values, colors, or geometry from outside by connecting them to the nodes inside. The group output node decides what data gets sent out of your node group or your geometry node setup. Only what you connect here shows up as outputs. This can include attributes, geometries, booleans, values, anything really. The next node is the warning node. This node basically outputs a custom message when an error occurs. It offers a drop-down menu which allows you to select what kind of message you want to output. This node allows you to guide your users of special node groups on what kind of input values are acceptable to the node group. The last node in this section is the viewer node. This node lets you see parts of a geometry node tree by only evaluating the nodes that come before it. The node updates both the geometry and the spreadsheet editor. When it's connected, the spreadsheet editor shows a custom column called viewer. You can view attributes by connecting them to the input values. Although the domain is automatically selected, there is a drop-down menu that allows you to select a custom domain. The next few nodes are called material nodes. These nodes are used to apply and manipulate materials. The first of these nodes is the set material node. This node basically assigns a material in a specified selection of your procedurally created geometry. Next is the replace material node. This node basically swaps one material with another. It has an input for the old material and an input for the new material which needs to be swapped. Next is the material selection node. This node provides a selection for all the meshes that use a specified material. Talk about the next two nodes, we need to talk about the material index. Each material in an object's material list has an index assigned to it. So basically, the set material index node and the material index node take advantage of this. The set material index node basically assigns an index to materials. The material index node retrieves these indices to be used in the geometry node tree. Coming up next, we got the UV nodes. The first of this node is the pack UV islands node. This node scales and moves UV islands to fill the UV space as efficiently as possible. It takes a UV map of selected faces as input and packs them together for the best fit. Margin defines the spacing between the UV islands. The next node is the UV unwrap node. This node generates a UV map based on a selection boolean of seam edges. It includes margin input to control the spacing between the UV islands and a fill holes checkbox which virtually closes the mesh holes, helping avoid overlaps and preserve the symmetry. The next set of nodes are called texture nodes. These are the same procedural textures that have been ported over from the shader editor. So I'll just quickly run through all of them. We got the brick texture node, the checker texture node, the Gabor texture node, the gradient texture node, the image texture node, magic texture node, noise texture node, Voronoi texture node, wave texture node, and white noise texture node. Mesh primitive nodes enable you to bring basic geometry shapes directly into the geometry editor. All nodes give the standard geometry and the UV map of the mesh as an output. Additionally, some nodes give the selection boolean of top, side, and bottom faces. So I'm just going to quickly roll over them since they all have the same function. Mesh nodes include, first we got the cone node, then we got the cube node, then we got the cylinder node. Up next we got the grid node, the icosphere node, the mesh circle node, the mesh line node, and the UV sphere node. The next set of nodes are called point nodes. These nodes deal with distribution, conversion, and generation of points. The first node in the list is distribute points in volume node. As the name suggests, this node basically distributes points in a given volume. It has two modes of operation, random or grid. In the random mode, it distributes points randomly in the volume based on a given density and seed. In the grid mode, it distributes points based on spacing input, which basically defines the spacing between two grid points, and a threshold input, which sets the minimum value of a volume cell to contain a grid point. Next is the distribute points on faces node. The name speaks for itself. It basically distributes points on selected faces. It has two modes of operation, random and Poisson disk. In random mode, it distributes points based on a given density and seed. In Poisson disk mode, it distributes points randomly on the surface while taking into account a minimum distance between 2 points which can be specified. The node has three outputs. One of the outputs is the generated point cloud itself, a normal output which gives the normal of the triangular face on which each point is scattered, and a rotation output which gives the rotation which is derived from the normal attribute of the point. Next is the points node. This node generates a point cloud with a given position field with points of a specific radius. Coming up, we got the points to curve node. This node generates a curve geometry by taking points and inserting them into a new curve. It takes in a point cloud as input, forming a curve between the points based on the order of the weight provided. Weight takes in any attribute. Weight basically serves as an ordering or an indexing input. The curve is created such that the starting points of the curve have the least weight, whereas the ending points have the most weight. The next in the list is the points to vertices node. This node creates a mesh vertex in the output geometry for every point in the input point cloud. Next we got points to volume node. This node basically creates a fog volume sphere around every point based on a density and a radius value. Next up we got set point radius node. This node controls the size of each selected point in a point cloud. Okay, the next set of nodes come under the read section in the geometry nodes part. The first of this node is the ID node. This node gives an integer value indicating the unique identifier linked with each geometry element in the point domain. It basically retrieves the ID attribute which we discussed earlier. Up next on the list, we have the index node. This node gives an integer value or the index indicating the position of each element in the list, starting from 0. Moving on, we got the normal node. This node outputs a vector showing the normal direction at each evaluated point. Coming up, we got the radius node. This node outputs the radius value at each point on the evaluated geometry. Next, we got the position node. This node outputs a position vector of each evaluated point in a geometry. The next set of nodes come under the sample section. The first of this node is the really powerful geometry proximity node. This node allows you to compute the closest location on a target geometry from a sample position. You can then split the input geometry into groups using the group ID input. The sample position defines the position used to calculate the closest location from. The sample group ID input allows you to select which group the closest element should be detected from. The node outputs the position value of the closest location on the target mesh. It also outputs the distance as a float point value from the source position to the closest location on the target. The isValid output tells whether the sampling was successful or not. It can fail if the sample group was empty. Next, we got the sample index node. This node allows you to retrieve a specific attribute from a source geometry at a given index. Value specifies the attribute that needs to be retrieved. Up next on the list, we got the sample nearest node. This node retrieves the index of the geometry element in its input geometry that is closest to the input position. This node is similar to the geometry proximity node, but it outputs the index of the closest element instead of its distance from a sample location. Moving on, we got the index of nearest node. This node returns the index of the nearest point for every other point in the geometry. It functions like the sample nearest node, but for every point within the same geometry. The position input is like moving the entire geometry from its original position to another position and then calculating the closest indices. The group ID input allows you to split the geometry to search for the nearest elements within singular groups. The hasNeighbor output gives a true value if the group contains at least two elements. Up next, we got the raycast node, another really powerful node that casts rays from one geometry onto another, finding hit points on the target mesh. The node outputs the normals, distances, and any specified surface attribute at each point. How these surface attributes are computed depends on the mode you set the node to. You can choose between two modes, interpolated mode and nearest mode. In the interpolated mode, it smoothly blends vertex and corner attributes, and in the nearest mode, it uses the value from the closest vertex without blending it. The node takes a position input which defines a starting point for the rays and a ray direction which defines the direction of each ray from the starting point. The ray length input sets the maximum distance a ray can travel before being considered as a no-hit. The is-hit output gives a true value if the ray intersects with the target geometry. The hit position gives the location of the intersection point on the target mesh. Hit normal provides the surface normal vector at the hit point. Hit distance represents the distance from the source position to the hit position. If no intersection occurs, it returns the ray length. The next set of nodes come under the right section. First of these nodes is the set ID node. This node fills the ID attribute on the input geometry. If the attribute doesn't exist, it creates a default value of 0. Moving on, we got the set position node. This node allows you to control the location of each point in a given geometry. The position input defines the new position of selected points. The offset input allows you to change the position of selected points. Next up, we got the set geometry name node. This node allows you to set a name for the input geometry. It overrides the name which might come from the object info node or the outliner. The next section is arguably the most important section in geometry nodes, so pay attention, kids. The first of this set is the bake node. This node saves and loads intermediate geometries for improved performance by baking parts of a node tree. It accepts various inputs such as geometries, attributes, vectors, booleans to be pre-calculated for later use. It has two modes of operation, still mode and animation mode. The still mode bakes data for a single frame and the animation mode bakes data for a custom range of frames. Next up, we got the bounding box node. This node creates a bounding box with the least volume that encapsulates the input geometry. It outputs the bounding box and the minimum and the max vectors which define the box extent in the x, y, and z axis. Next up, we got the convex hull node. This node outputs the convex hull of a given geometry. Moving on, we got the delete geometry node. This node removes selected parts of a geometry. The domain specifies the type of elements to delete. This can be point, edges, face, spline, or instances. Coming up next, we got the duplicate elements node. This node creates new geometry by duplicating the input geometry a specified number of times. The position of the elements remain unchanged, so all duplicates will be at the same location. The domain setting specifies the type of elements to duplicate. This includes points, edges, faces, or splines. The node outputs a duplicate index, which basically assigns an index to each duplicate, with the original geometry getting an index of 0 and subsequent duplicates getting a +1 value. Moving on, we got the merge by distance node. This node takes in input geometry and merges vertices or points within a specified distance. This node is similar to the merge by distance operator or the weld modifier. Next, we got split to instance node. This node basically splits up geometry elements into instances based on a group ID. Next up on the list is the sort elements node. This node rearranges geometry elements by changing their indices. The sorted weight is used as a sorting criteria, typically based on an attribute. Coming up is the transform geometry node. This node moves, rotates, and scales the entire input geometry. Unlike the set position node, which moves individual points, this node applies a transformation to the whole geometry. The node provides two methods to apply the transformation: by components, which provides separate input for location, rotation, and scale, and by matrix, which allows the node to take in a transformation matrix as an input to apply transformation. Next up, we got the separate component node. This node splits an input geometry into its individual components. These components include mesh, curves, grease pencils, point clouds, volumes, etc. Moving on, we got the separate geometry node. The separate geometry node produces two geometry outputs based on the selection input provided. The selection outputs the selected geometry and the inverted outputs the not selected geometry. The next section is the miscellaneous category. These are just nodes which are not under any section in the list. First in this list is the joint geometry node. This node basically merges separately generated geometries into a single bigger geometry. Up next on the list is the geometry to instance node. This node converts multiple input geometries into instances. Unlike the joint geometry node, which merges the geometries, this node outputs separate instances without combining the geometry data. This node is more efficient than the joint geometry node for large geometries, as it avoids creating a larger mesh or a curve.
The next set of nodes are called utility nodes. Most of these nodes have been bridged over from the shader editor. So if you have any idea of what these do in the shader editor, you have the entire grasp of what it does in the geometry nodes. The first of these nodes is the black body node. You know how when you heat up an object, it starts glowing a red hot color? Well, this node is supposed to simulate that. It basically gives the color output that corresponds to the color emitted by a body at a specific temperature. Next is the color ramp node. If you have any idea of what it does in the shader editor, it basically does the same thing in geometry nodes. Next, we have the combine color node. This node combines individual channels into one color image. It can take color channels in the form of RGB, HSV, or HSL. It also has an alpha channel as input to control opacity. Next up, we have the separate color node. This node basically separates an image into its elemental channels. Next up, we have the RGB curves node. This node can perform level adjustments on each color channel or on all the color channels as a whole. The next set of nodes come under the text category. Their main functionality is to act upon and manipulate strings. First in this set is the string to curves node. This node converts a text input into curves. This node is highly optimized. If a character is typed once, then it is realized as an actual curve, and then the subsequent use of the same character makes instances which help the node in being memory efficient. The node has several options such as font, size, character, spacing of characters, word spacing, etc. All the options one might find in a text editor to format the text. The node outputs instances, so you'll need to realize them before you start operating on them. The next node is the join strings node. This node combines any number of input strings into one single string. The order of strings depend on the vertical ordering of the inputs in the multi-input socket. The node also provides a delimiter, which basically adds another string in between the input strings. Next is the replace string node. This node replaces a string segment into another string. The next node is the slice string node. This node basically allows you to extract a string segment from a larger string. How this does that is by taking the starting position of the slice in the larger string and the length of the slice. Next is the special characters node. This node is used to output string characters that can't be directly typed with the keyboard. Last of the text nodes is the value to string node, which basically converts a numerical value, which could be a float or an integer, to a string. It has a decimal input to set the precision of the numerical output. The next set of nodes are the vector utility nodes. First in this is the vector curves node. This node takes a vector as input and maps it to a curve. The next node is the vector math node, which basically does vector math. The next node is the vector rotate node. This node takes a pivot point as an input and allows you to rotate a vector above that pivot point. The next node is a combine XYZ node, which combines individual X, Y, and Z components into a single vector. The next node is a vector mix node. It has two modes of factoring, uniform and non-uniform. In the uniform mode, a single float value controls the blend between two vectors. In the non-uniform mode, you can control the blend between individual XYZ channels of two vectors separately. Next, we have the separate XYZ node. This node breaks a vector into its individual XYZ components.
Before we move ahead, I think it is important for us to understand how a simple operation as rotation takes place in a 3D space. Basically, rotation in Blender can be represented in three forms: the Euler form, the vector axis form, and the quaternion rotation form. In the Euler form, rotation is represented by angles about the x, y, and z axis. The order in which these angles are read/written matters a lot. So angles written in the x, y, z format is very different from angles written in y, z, x format. This form of rotation is very intuitive to understand, but suffers from a major flaw: gimbal lock, causing rotational problems during keyframing. The next form of rotation is vector axis form. This form lets us define an axis and a rotation angle W around that axis. This method is not that intuitive and also suffers from the problem of gimbal lock, and so it's hardly used. The next form of rotation is the quaternion form. Quaternion rotation uses 4 values to represent 3D rotations: X, Y, Z, and W. The best way to describe how quaternion rotations work is that they describe the state of orientation of an object. Unlike Euler angles, quaternions avoid gimbal lock and provide smooth and continuous rotation. The only con of quaternion rotations is that they are really unintuitive and they don't make sense at all. Right, now we can move on to the rotation nodes. The first of this node is align rotation to vector node. This node basically aligns a specified axis to a specified vector. The top axis input defines which axis should be aligned. The vector defines the direction in which the axis should be aligned. Pivot basically locks up the rotation to only rotate about a specified axis. Next up, we got axis to rotation node. This node basically allows you to create a rotation based on the direction of two axes. The node allows you to select which two axes. The next few nodes are called point to the primary direction and the secondary direction, which are both specified using direction vectors. Next, we got axis angle to rotation node. This node allows you to create a rotation based on the direction of a single axis and an angle about that axis. It's similar to the vector axis form we were talking about earlier. Next, we have Euler to rotation node. This is a pretty self-evident node. It creates a rotation depending on the Euler rotation values. Next is the invert rotation node. This node inverts a given rotation. Inverting is the same as adding a minus sign to your rotation. Next is the rotate rotation node. Yeah, that's the real name. This node adds a specified amount of rotation to an already given amount of rotation. The node offers the choice to rotate about the local or global space. Next is the rotate vector node. This node allows you to rotate a vector by a given amount. The output is in the form of a vector. Next is the rotation to Euler node. This node converts a given rotation to standard Euler form of rotation. Next is the rotation to quaternion node. This node converts a given rotation to the standard quaternion form of rotation. Next is the quaternion to rotation node. This node converts a given quaternion rotation to standard rotation form. The next set of nodes are deprecated nodes. Don't use these nodes at any cost. The two nodes in this are Euler to rotation node and rotate Euler node. Their replacements already exist in the current collection of nodes, and these nodes are just basically outdated legacy nodes. They exist so that older versions of Blender can be easily imported into newer versions of Blender without breaking the file.
The next set of nodes we are going to cover are called import nodes. These nodes allow you to bring in external data into the geometry node editor. The first node we will look at is the import CSV node. This node lets you bring in CSV files and turn them into a point cloud, which allows visualizing external data in geometry nodes. It takes in a file path and a delimiter, which is a character that splits the values inside the file. Up next is the import OBJ node. This just lets you bring in OBJ files directly into the geometry node editor. It only imports the 3D models. Materials and textures are ignored. Up next we got the import STL node. This node brings in mesh geometry from a .stl file. These files are common in 3D printing and CAD softwares. They only store surface geometry, usually in triangles with no color, texture or extra attributes. Up next we got the import PLY node. This node brings in mesh data from .ply files. These files usually come from 3D scanning or modeling software and can include vertex attributes such as colors or normals. Up next we got the import text node. This node reads plain text files and spits out the entire content as a single string. And the last node in this list is the import VBD node. This node loads volumetric data from a .vbd file and it outputs it as a volume geometry. It allows you to bring in simulation data or volumes made in other software directly into geometry nodes.
Matrix nodes, these are advanced math heavy nodes. Stay in school, kids, it makes you better at Blender. A transformation matrix is a 4x4 matrix, which means it has 4 columns and 4 rows. This kind of matrix allows for an intuitive and a computationally efficient way to translate, scale, rotate, and skew objects in 3D space. The first of these nodes is the combined matrix node. This node constructs a 4x4 matrix from its individual values. Next is a combined transform node. In Blender, transformation, rotation, and scale can be represented in the form of vectors. These vectors can be represented as columns in a matrix. This node just enables you to create that matrix. Next is the invert matrix node. Inverting a matrix is a mathematical operation and this node just enables that. Next is the determinant matrix node. Determinant is a value that can be derived from any square matrix and this node just allows you to find that. Next is the multiply matrix node. This node just allows you to multiply two matrices. Next is the transform direction node. This node allows you to multiply a transformation matrix with a given direction vector. In practice, this node basically allows you to transform an object by manipulating its transformation matrix. Next is a separate transform node. This node basically allows you to separate a transformation matrix into its translation vector, rotation vector, and scale vector. Next is the point project node. This node applies a projection matrix to a point. This node is particularly useful when you're messing with perspective. Next is a transform point node. This node applies a transformation matrix to a position vector. Next is a transpose matrix node. Transposing a matrix is a mathematical operation and this node just enables that. The next few nodes are categorized as topology nodes. These nodes help in accessing topology of a mesh at an index level. They function in a very similar fashion and hence I will explain one of them in a very detailed manner and then extrapolate the explanation for the rest of them. The first node we'll be looking at is the corners of edge node. This node outputs the index of a corner in a selected edge. The node uses the edge index to select edges and only finds the corners of those edges. After the edge returns its corners, they are unordered and grouped together. They need to be sorted for easier access. To do this, we use the weight input. You provide an attribute to this input and the node sorts the corners by that attribute, assigning them indices in descending order based on their weight. Now the corners can be accessed using the sort index assigned by the node. The higher the sort index, the smaller the weight. The outputs of this node include the corners index and the total corner count. Up next we got the corners of face node. This node retrieves the corners of specified faces. The output of this node is the number of face corners and the corner index.
Before we take on the next part, I think it is important for us to understand what's the difference between a corner and a vertex. At first glance, a corner and a vertex might appear to be the same thing, but that's not the case in Blender. A vertex in Blender is just a point in 3D space, and that's all there is to it. Whereas a corner, or more specifically a face corner, is that same point belonging to a specific face. So suppose you have a cube and you select one of its corners, that point is connected to three faces. So even though it has one vertex, it represents three face corners, one for each face it's part of.
Next is the corner of vertex node. This node retrieves corners adjacent to the specified vertex. The output of this node is the number of adjacent corners and the corner index. Moving on, we got the edges of corner node. A face corner is always shared by only two edges. So this node retrieves the edges on both sides of a face corner. Up next, we got the edges of vertex node. This node retrieves the edges connected to a vertex.
Next, we got the face of corner node. This node retrieves the face which is attached to a face corner. Its outputs include the index of the face itself and the index of the corner within the face.
Next is the offset corner in face node. This node retrieves another corner in the same face as the input corner. This is similar to the offset point in curve node. And the last node in this section is the vertex of corner node. This node outputs the index of the vertex that a face corner is attached to. The next set of nodes are called utility math nodes. First of this is the Boolean math node. This node basically performs basic logical operations on its inputs. These operations include AND, OR, NOT, etc. Next is the clamp node. This node takes in a value and sets a maximum and a minimum range the value can take. Next is the compare node. This node takes in two inputs and compares them to give a Boolean output. The node works on all data types including but not limited to float, vector, color, etc. Each data type has its own data specific operations, like when the node set to color mode has an operation called lighter or darker, which compares which of the two color inputs is lighter or darker. Next is the float curve node. This node basically maps an input float value to a curve. Next is the float to integer node. As the name suggests, the node basically converts a float value to an integer. Next is the hash value node. This node takes an input value and hashes it to an integer. Hashing means to convert an input value, that is a number or string or any set of data, into a unique fixed sized integer using a hash function. This process ensures the same input always produces the same integer, but small changes in the input can produce drastically different integers. It is often used in the task of indexing, data mapping, or ensuring unique identifiers. Next is the map range node. This node remaps a value range to a target range. It offers several methods of interpolation between two ranges. These include linear, step linear, smooth step, smoother step. Next is the math node. This node is a really powerful node as it includes many math operations that can be applied to various inputs. The next set of nodes, I have categorized them under the miscellaneous category because they don't particularly fall under any pre-written existing category. So the first of this is the for each geometry element zone. This zone type basically allows you to run a loop of operations for each element of an input geometry. Zone takes in standard geometry as an input. It can also take any attribute as an input that needs to be accessed during the loop. The element output inside the zone gives separate geometry for each element for the current iteration the zone is in. It also offers the choice to select the domain of geometry it should iterate over. The index output inside the zone gives the index of the geometry element. The outputs of the zone include the main geometry, which gives the same geometry that was plugged into the input, and the generated geometry, which outputs the mesh that was generated after the zone operated on it. Next up, we got the menu switch node. The menu switch node outputs one input based on a menu selection. Only the selected input is computed. You can define what the menu entry should be and what operation is behind each menu entry. Next up on the list is the index switch node. This node is like scrolling through a menu of outputs. To select a particular output, you choose a corresponding number, which is the output index. It has an advantage over the menu switch node. That is because this node can allow you to select multiple options, which cannot be done in the menu switch node. Next up is the random value node. This node outputs a random value for a given range of numbers. It has four modes: float, integer, vector, and boolean. It has a seed value input, which can be used to generate more variation. In the Boolean mode, the node has a probability input, which decides the probability of whether the output will be true or false. Next up, we have the repeat zone. This zone loops a set of operations on the selected input geometry for a specified number of iterations. The current iteration the zone is in is available using the iteration input on the inside of the zone. Next up on the list is the switch node. This node outputs one of two values depending on the switch checkbox. When the checkbox is ticked, the true value is sent through, and when the checkbox is not checked, the false value goes through. The next section of nodes come under the read section in the curve nodes. Before we start, I think we need to understand the difference between a curve and a spline. A curve basically contains multiple splines, and a spline is basically a mathematical formulation of a curved line or an object. The first of these nodes is the curve handle position node. This node outputs the position of the handles of a Bezier spline. The left gives the position of the left handle and the right gives the position of the right handle. If the curve does not contain any Bezier spline, the node will output 0. Selecting the relative checkbox outputs the handle positions relative to the corresponding control point. Next is the curve length node. This node outputs the length of all the splines added together. Basically gives the total length of a curve. Next is the curve tangent node. This node outputs the direction that a curve points in at each control point. Next is the curve tilt node. This node outputs the angle used to turn the curve normal around the curve tangent on the evaluated points of a curve. Moving on, we got the endpoint selection node. This node provides a selection for an arbitrary number of endpoints in each spline in a curve. The start size controls the number of points to select from the start. The end size controls the number of points to select from the end. Up next on the list is the handle type selection node. This node creates a selection filter based on the handle types of each control points. The node provides left or right mode, enabling anyone, checks only the handle of that side. Enabling both makes the node give true value if either of the two handles is the chosen type. Next up is the isSpline cyclic node. This basically tells whether each of the curve splines are cyclic or not. Coming up, we got the spline length node. This node outputs the total length of each spline as a distance or a number of points. This is different than the curve length node, which adds up the total length of all the curve splines. Moving on, we got the spline parameter node. This node basically outputs how far along a control point is in the spline. The factor output basically maps a 0 to the starting point of the spline and a value of 1 to the end point of the spline, and then interpolates the value for all the control points in between. The length output gives the distance of each control point from the starting point. The index output outputs each control point's index on its spline. It's different from the index node, which also counts the control points in all the previous splines. The last node in this set is a spline resolution node, which basically outputs an integer value that corresponds to the number of points that will be generated between two control points, which basically mean it outputs the resolution of the spline. The next node is the only node in this section called the sample curve node. This node calculates a point on a curve at a certain distance from the start of the curve, specified by the length or the factor input. It is used to output the data retrieved from that position on the curve.
The next nodes we are going to cover are called tool context nodes. These are special kind of nodes that are only available in the geometry nodes tool editor. Well, what is the tool editor, you might ask? If you see, there are two types of geometry node editors. First being the regular one, which we call the modified geometry nodes, and the other being the tool editor. The regular ones are called modified geometry nodes because these run procedurally and repeatedly as part of a modifier system, which you can see in the modifier stack if you go into the properties panel. The second one is called the tool editor. These are different because they only run once and apply their effect immediately, causing destructive changes. Any tool you create in the geometry node tool editor is then available here, and it executes its function only once when clicked. The tool editor comes with some special nodes that aren't available in the regular geometry node editor, and these nodes are basically called the tool context nodes. On top of that, the tool editor workspace offers some options which aren't available in the regular workspace. These being the types, which allows you to select which type of geometry the tool will work on. These include mesh, hair curves, grease pencil, and point clouds. Next being the modes. This defines the workspace where your geometry node tool will work. It can either be the object mode or the edit mode or the sculpt mode. And the next special option the tool editor workspace provides is the option to wait for a click, which as the name suggests, the tool will listen for a click before initiating. So now let's jump into the nodes which are only available in the tool editor. The first being the 3D cursor node. This node allows you to bring in the information of the 3D cursor into the geometry node editor. This node outputs the location and the rotation values of the 3D cursor. Up next, we got the mouse position node. This node provides the location of a mouse cursor. The mouse X and Y give the cursor's region space coordinates in pixel. The region width and height output the total size of the region in pixels. Up next, we got the self object node. This node outputs the object that contains the geonode setup. This is usually used to retrieve the original transforms of an object. Coming up, we got the view transform node. This node retrieves the view direction and the location of the 3D viewport. The projection output provides the viewport's projection matrix. The view gives the direction and the location of the 3D viewport in matrix form. The is orthographic output gives a boolean true or false indicating whether the viewport is using an orthographic projection or not. Coming up, we got the selection node. This node outputs true for the geometry which is selected in edit mode and false if it's selected elsewhere. It can also give the selection in the form of a float value, which means if the geometry is selected in edit mode, it gives a float value of 1, and if it's not, it gives a float value of 0. Coming up, we got the active element node. This node outputs the index of the active geometry element in the specified domain, and the exists output gives a true value if an active element exists in the mesh and false otherwise. Up next, we got the set selection node. The set selection node allows you to control which geometry is selected using the selection node as input. It basically allows you to hold the geometry selection you make throughout the node tree. Up next, we got the face set node. The face set tool in sculpting mode allows you to group faces by coloring the faces you want to be in the same group with the same color. This node outputs the face set index, which shows which face belongs to which set. Faces in the same set have the same integer value. The Boolean output indicates whether any face sets exist or not. And the last node is the set face set node. Yeah, that's a mouthful. This node assigns selected faces to a face set, which is specified using the face set input, which basically acts as a group ID input. Coming up, we got the Gizmo nodes. Gizmos are basically an interactive tool in Blender that allows users to control geometry node inputs directly through the 3D viewport. All gizmos share common input and outputs, which I'm going to explain once. The first being the always visible button. This ensures that the gizmo remains displayed in the 3D viewport even when the associated node is not selected. Up next, we got the colors. All gizmo nodes have a drop-down menu to select the color of the gizmo in the viewport. Up next, we got the outputs. Every gizmo gives a transform output, which is basically the gizmo's transformation as a matrix. It is useful for making the gizmo move in sync with the geometry it affects. Up next, we got the value. This is a bidirectional input, which means it gives in an input and gives an output. Using this input implies that moving the gizmo in the 3D viewport updates the connected input values, while adjusting the input values in the node editor updates the gizmo's position in the viewport. Now, since we have covered the common inputs, let's dive into the specific gizmos that are available. First, we have the dial gizmo. This is basically a circular ring. This node allows you to create angle changes. Position sets the position of the gizmo. Up defines the direction in which the top side of the gizmo will point. The screen space checkbox, when checked, keeps the gizmo size constant regardless of the level of the zoom in the viewport. Radius sets the radius of the dial. Moving on, we got the linear gizmo. This node creates a gizmo that moves linearly. The position sets the position of the gizmo, and the direction specifies in which direction the gizmo will point to. And the last gizmo node we have is the transform gizmo. This node has the ability to control the position, rotation, and scale of the object it is applied to. The position input is used to set the position of the gizmo, and the rotation input sets the rotation of the gizmo. Okay, the next set of nodes are called mesh operation nodes. The first in this set is the dual mesh node. This node transforms a mesh by placing a vertex at the center of each face, and these vertices are connected to form a new mesh, discarding the original geometry. The next three nodes I'm about to cover have almost the same functionality. The first node I'm talking about is the shortest edge path node. This node finds the shortest path along mesh edges, leading to selected set of end vertices. This is done by assigning a cost to each edge. By default, the cost is set to 1, but this can be customized using the edge cost input. The shortest path is the one with the lowest total cost to travel. The end vertex input defines where the edge paths will end. The next vertex index, which is a field which gives the index of the next vertex along the selected shortest path. This node is usually paired with the edge paths to curves node or the edge paths to selection node. These both nodes are similar, just one of them gives selection booleans and the other one gives in curves. These both nodes take in start vertices which work in conjunction with the end vertices of the shortest edge path node to define the start and the end of the edge path we are trying to select. Up next, we got the extrude mesh node. This node lets you extrude selected parts of the input geometry. It also allows you to choose the domain where the extrusion should occur. The extrusion can be restricted to a specific direction using the offset vector, which by default follows the element's normal direction. The offset amount controls the amount of extrusion that should occur. The individual checkbox allows you to extrude each face separately instead of extruding connected faces as a group. The node outputs the extruded geometry along with the selection boolean fields for the top and the side faces of the extruded geometry. Up next is the flip faces node. This node reverses the order of vertices, which causes the face to be flipped. The most common use of this node is to flip the normals of a face. The next node in the list is a very powerful node called the mesh boolean node. This node is a direct replacement of the boolean modifier. It has standard boolean operations such as difference, union, and intersect. It takes in multiple meshes through the mesh 1 and mesh 2 input. It has three solvers within it. The first is float, which is fast but has some problems in certain edge cases such as overlapping geometry. Next is the exact solver. This is the most complex solver and it takes the most time. However, this is the most accurate. And the last is the manifold, which is the fastest and really accurate, but only for watertight meshes. Moving over to the mesh 2 points node. This node creates a point cloud from all the selected vertices of a mesh. The radius input controls the size of the points in the viewport. The position input allows for adjusting the location of the points. Coming up to the mesh to volume node, this node creates a volume grid based on the input geometry's shape. The density input
allows you to set the voxel value inside the generated volume. It has two modes of resolution, amount and size. In the amount mode, you can specify the approximate number of voxels along the diagonal of the bounding box, and in the size mode, it specifies the side length of the voxel. The interior bandwidth controls the maximum distance of the included voxels to the mesh surface on the inside. Next is the scale elements node. This node scales connected geometry groups based on the specific value from the scale input. The node takes center as an input, which defines the position of the point around which the geometry will be scaled. By default, is the center of mass of the object. The node offers domain selection to choose between scaling on edges or faces. The node also provides the option for uniform scaling or scaling along a single axis defined by the direction vector. Coming up, we got the split edges node. This node functions like the edge split modifier, basically splitting and duplicating edges within a mesh. The node takes in geometry as an input and splits the edges of selected groups. Moving on to the subdivide mesh node. This node subdivides a given input mesh by adding new faces. It uses simple interpolation for mesh deformation. It's similar to the subdivision surface modifier set to the simple mode. Up next, we got the subdivision surface node. This is similar to the subdivision surface modifier set to the Catmull-Clark mode. The node has a level input, which allows you to control the amount of subdivision that takes place in the mesh. The edge creases and the vertex creases allow you to control the smoothness on edges and vertices. This is done using the sharpen function in the edit mode. The node also offers various options to control how the subdivision will affect the final UV map of the mesh. The limit surface checkbox places new vertices such that the surface that will be produced has the smoothest possible shape. Up next, we got the mesh to curves node. This node basically converts meshes into curves. It has two modes of operation, edges and faces. In the edge mode, it converts every edge of the mesh into a different spline, and in the face mode, converts every face of a mesh into a cyclic spline. The last node in the list is a triangulate node. This node basically converts n-gons and quads in a mesh into triangles. It has several methods to do this, and each method's description is given here. Up next, we got the volume nodes. The first node in this list is the volume to mesh node. This node generates a mesh from a given volume. This node has several methods to control the resolution of a mesh. First being the grid method, which makes the resolution of the mesh generated dependent on the resolution of a 3D grid. Next being the voxel amount method. This specifies the approximate resolution of the final mesh depending on the number of voxels we want in the final mesh. And the last being the voxel size, which uses a fixed size of the voxel to generate a mesh. Threshold input defines the minimum amount of the density of a voxel to be considered while generating a mesh around it. The adaptivity input reduces the final face count by simplifying geometry where detail is not needed. The last node in this section is the volume cube node. This node generates a 3D volume grid based on a density provided. The min and max input define the bounds of the cube generated. The resolution input defines the number of voxels to evaluate on each axis. The background input sets the grid value outside the cube, improving memory efficiency if it matches the density value. The next section is the right section. First node in this section is the set curve normal node. This node allows you to control the method used to calculate curve normals. The methods offered by this node are minimum twist, Z up, and free. In the minimum twist method, the normals are automatically calculated such that the twist around the curve tangent is minimum across the whole curve. In the Z up method, the normals are calculated such that they are perpendicular to the global Z axis. In the free method, the node allows you to set custom directions for your normal. The next node in the list is the set curve radius node. This node allows you to control the radius of the curve set for each control point, and this radius is then interpolated across every evaluated point in between the control points. Coming up, we got the set curve tilt node. This node controls the tilt at each control point of the curve. The tilt of a control point is the angle between the normal of that point and the tangent at that point. Moving on, we got the set handle position node. This node sets the position for the handles of Bezier curves. The node offers the left-right mode, which controls the position of either left or right handle position. Coming up on the list, we got the set handle type node. This node sets the handle type for the points on the Bezier curve. This node also offers the left-right selection for setting the handle type. Up next, we got the set spline cyclic node. This node controls whether each spline will loop back on itself, creating a cycle. When you enable the cyclic option, a connection will be made between the first and the last control point, which will be visible in the viewport and the final render. Next is the set spline resolution node. As the name suggests, this node sets the resolution of a spline curve. It does this by setting the value for how many evaluated points will be generated between every control point on the curve. Next up, we got the set spline type node. This node basically sets the spline type, which could be poly, Catmull-Rom, Bezier, or NURBS. The next set of nodes come under the operations section. The first of this is the curve to mesh node. This node converts all splines of a curve to a singular mesh. Optionally, a profile node can be provided to give the curve a custom shape. The curve also provides a fill cap option to put faces at the ends of the curve. Moving on, we got the curve to points node. This node generates a point cloud from a given curve. The node provides several methods of sampling points on the curve. The methods include count, length, and evaluated. In the evaluated mode, the node gives a point cloud generated from all the evaluated points on the curve. In the count mode, the node samples each spline and evenly distributes a specified number of points. The length mode samples each spline by splitting it into segments with a specified length. The length will be rounded down so that a whole number of samples will fit into each spline. Next up, we have the curve to grease pencil node. This node converts a top level curve to a grease pencil layer. If the instances as layers is checked, then realized geometry is ignored and each instance of curves are converted to a separate layer in grease pencil. Up next on the list is the deform curves on surface node. This node is used to adjust the position and the rotation of curves based on the changes in the surface they are attached to. This node is mainly used to create hair systems so that the hair react and follow the surface they are attached to. Next is the fill curve node. This node is basically used to fill the faces in a cyclic spline. It has two modes, n-gon and triangle. As the name suggests, the n-gon mode fills the faces with n-gons and the triangle mode fills the faces with triangles. Next is the fillet curve node. This node rounds corners on curve control points, similar to the effect of the bevel modifier on a 2D mesh. However, a key difference is that the rounded portions created by the node are always portions of a circle. It has two modes, Bezier and Poly. In the Bezier mode, only two control points will be generated for every fillet point, and in the poly mode, the number of control points generated for each fillet point is directly dependent on an integer field input.
Up next, we got the resample curve node. This node takes in a standard curve as input and creates a new polyspline from it. It does this by adjusting the number of control points present in the curve. It has two modes, count and length. In the count mode, it generates a specified number of points spaced evenly in the curve. In the length mode, it spaced control points evenly using the specified length. This decides the resolution of the polyspline which is generated.
Moving on, we got the reverse curve node. This node swaps the start and the end of the spline. The shape of the spline does not change though. Next is a subdivide curve node. This node adds more control points in between existing control points. The cuts input defines the number of control points to be created on the segment following each point. It is different from the resample curve option because the resample curve turns the existing curve to polysplines, whereas this node leaves the spline as it is. Moving on, we got the interpolate curves node. This node generates a new curve on specified points by interpolating existing curves. As input, it takes in curves to use as guide curves and point clouds as points to distribute on the curves. The guide up input is a surface normal vector, which when you supply this improves the quality of interpolation.
The closest index output gives the index of the closest guide curve from every other curve in the geometry. The closest weight basically tells how far away a curve is from its closest guide curve.
The last node in this section is the trim curve node. This node shortens each spline in the curve by removing sections at the start and the end of each spline. It has two modes, length and factor. The factor mode finds the position of new endpoints by giving you the option to choose a value between 1 and 0. The length mode finds the endpoint positions using a length from the start of each spline. The input values should be between 0 and the length of each spline. The next set of nodes are called curve topology nodes. The first of this set is a curve off point node. This node takes in the value of a control point and retrieves the index of the curve it is a part of. Moving on, we got the offset point in curve node. This node allows you to retrieve other control points from an input control point. It takes in the index of an input control point and an arbitrary integer as the offset, which is basically the number of points to move along the curve before finding the result. If the curve is cyclic and the offset goes past the start or the end point of the curve, it will wrap around to the other side. The isValid offset output checks and outputs true or false based on if the offset provided does not exceed the number of control points in the curve. The last node in this section is the points of curve node. This node retrieves indices of specific control points in a curve. It takes in the index of a curve, a sorting weight, and a sorting index. The sorting weight is like a sorting filter, usually an attribute used to arrange the control points. The sorting index specifies which sorted point needs to be given as an output in the point index output. The total gives the number of control points in the curve.
The next set of nodes we are going to cover are called grease pencil nodes. The first of this set is the named layer selection node. This node allows you to select and isolate layers by entering the layer's name in the input field. Moving on, we got the set grease pencil color node. This node allows you to change the color and the opacity of a grease pencil object. The node has an option to select whether the grease pencil object is a stroke or a fill object. Up next, we got the set grease pencil depth node. This node allows you to order the grease pencil layers. It has two modes, 2D and 3D. In 2D layer mode, the layers follow the order in the 2D layer list from the top to bottom, ignoring their actual position in 3D space. In the 3D layer mode, they follow their order based on their position in 3D space. Up next, we got the set grease pencil softness node. This node lets you control how soft or sharp a stroke's edge will appear. Higher values make the edges more transparent and blurry, while lower values keep them sharp and clean. Up next, we got the grease pencil to curves node. This node converts a grease pencil setup to curves. The layers as instance option converts each layer into a new instance of curves, letting you work with them in a curve-based node system. The last node in this list is the merge layers node. This node combines grease pencil layers into a singular layer. It offers two methods to determine which layers to merge. The first option being by name, which combines all layers with the same name into a singular layer, and by group ID, which uses a custom group ID input, and all the layers with the same ID are merged together in a singular layer.
The next set of nodes are called hair nodes. These nodes are used to create hair systems all through geometry nodes. Most hair nodes have inputs which are repeated across every node, so I'm going to explain them once here. The factor input controls the effect of the node on the current hair system. 1 applies the effect on the node completely and 0 negates the effect of the node. The geometry input takes in standard geometry as input, but hair nodes only affect the hair curves and not the geometry the hair is attached to. The shape input controls how the effect of the node is applied across the length of the hair curve. A value of 0 has a constant fall off of the effect, and a value of 0.5 has a linear fall off. The preserve length input preserve each curve's length during deformation. The first section we will look at, which are called generation nodes. The first of this section is the duplicate hair curves node. This node duplicates hair curves a specified number of times within a given radius. The radius input defines the area where the duplicates are created. The amount input sets the number of duplicates per curve. Viewport amount displays a percentage of duplicates in the viewport. This is done to improve viewport performance. Distribution shape describes how strands are distributed within the radius. The tip roundness offset curves so the duplicated strands form a rounded tip. The even thickness input distributes the strands evenly across the radius. Next up, we got the generate hair curves node. This node creates new hair curves on a mesh surface. The node requires a surface object for generation, and this can be provided through the surface geometry input or the surface object input. The node also requires a UV map of the surface to find points of the location of the roots using UV coordinates. The surface rest position checkbox sets the mesh to its rest position before attaching curves. It's like applying scale, rotation, or location before adding a modifier to it. The hair length, material, and density define how the hair will look on the surface. The control point input sets the number of points in the curve. More points smoothens the curve but increases computation cost. The Poisson disk checkbox distributes control points randomly on the surface while taking the minimum distance between points into account. The density mask input is used to customize the density of the hair on the mesh surface. This is done using weight paints. The mask texture input is used to mask out control points using a texture image. The viewport amount allows you to display a percentage of the final number of hair strands in the viewport. This is done to better viewport performance. The outputs of this node include the geometry, the curves generated, and the surface normals. The surface normals give the direction of the normals on the position of the root of the hair curves. The last node in this section is the interpolate hair curves node. This node creates hair curves by interpolating between existing guide curves on a mesh surface. The follow surface normal node aligns the interpolated curves to the surface normal. The part by mesh island node uses mesh islands for parting the interpolations. The distance to guide input specifies the distance around each guide to spawn interpolated curves in. The next section are called deformation hair nodes. The first node in the list is the blend hair curves. This node blends hair curves between guide shape curves. Blend radius defines the area around each guide curve to consider for blending. Blend neighbors sets the number of neighboring guides to include in the blending calculation. Up next, we have the displace hair curve node. This node basically displaces hair based on an input vector. The vector used to define displacing direction can be obtained in three ways. The first way is using the vector input. In this, you can directly define the displacement direction using a vector. Next is the surface input. In this method, you specify a surface and provide a surface UV map. And by providing these two inputs, the node calculates the normal direction at the point of attachment of hair curves that will be used to displace them. The amount of displacement is then controlled by the surface normal displacement input. And the third and the final way is by using the object space. In this, you can select any object and rotating it around will define the vector direction that will displace the curves. Up next, we got the frizz hair curves node. This node deforms hair curves to create a frizz effect by rotating each control point along a random vector. The distance input controls how far along the strand the effect applies. The cumulative offset, when enabled, carries the offset of one point to the next. The offset vector input provides the vector used to offset each point during deformation. Moving on, we got the hair curve noise node. This node deforms hair curves using a noise texture. The hair curves noise node and the hair frizz node share almost the same outputs and inputs, and visually they do the same thing, but under the hood, the frizz hair nodes uses random vectors per point to deform a hair curve, whereas a noise hair curve node uses a noise texture to deform the hair curve node. The scale input adjusts the scale of the noise texture relative to the root position. The scale along curve input modifies the scale of the noise texture along each curve's length. The offset per curve input adds a random noise offset for each curve. Up next, we got the roll hair curves node. This node rolls hair curves along their length. The subdivision input specifies the subdivision level of the hair before deformation. Variation level controls the smoothing of the roll path. Roll length, radius, depth, and taper define the shape of the rolled hair. Retain overall shape offsets the roll along the original curve to preserve its original shape. Roll direction takes a vector input to set axis around which each curve rolls. Random orients and adjusts the randomness of the roll direction. Up next, we got the rotate hair curves node. This node basically rotates the hair curves around a specified axis. The axis input allows you to specify which axis you want to rotate it about. By default, it rotates to the normal, which is positioned at the root of the hair curve. The angle input lets you specify how much you want to rotate the hair curve. The random offset brings in randomness to your rotation. The lock ends basically locks in the position of the tip and the root of the hair curve. This basically means you're rotating about an axis which passes through the tip and the root. Moving on, we got the shrink wrap hair curves node. This node shrink wraps hair to a mesh surface. The offset distance sets how far from the surface the hair should be shrink wrapped. Above surface input blends the shrink wrap effect from points above the surface. The smoothing step controls the number of smoothing iterations applied after the shrink wrap. Lock roots keep the roots of hair curves fixed in position. Up next, we got the smooth hair curves node. This node smooths the shape of hair curves. The amount input controls the smoothing intensity. Negative values create a crumpling kind of effect. The iteration input determines the number of smoothing steps to be applied. The weight input acts as a factor to influence the smoothing effect. Lock tips keeps the tips of the hair nodes fixed in position. Coming up, we got the straighten hair curves node. This node straightens hair curves while keeping the tips and roots fixed in position. Amount controls the degree of straightening. Negative values cause the curves to crumple. The last node in this section is the trim hair curves node. This node trims or scales hair strands to a specific length. Scale uniform scales each curve evenly to the target length. Length factor multiplies the original length by a factor. The replace length input sets the strand to a fixed target length. The random offset trims strands randomly within a specified range. Mask input applies a mask to control this effect. The pin at input offsets the root and the entire trim strand along the curve. The next section is called read nodes. The first of this section is the curve info node. This node gives vital information about each curve, such as curve index, curve ID, length, and direction. Surface UV returns the UV coordinates of each curve's attachment point. Next is the curve root node. This gives information about the root of each curve. Root selection gives a Boolean value of the root points. Root position returns the position vector of each root point. Root direction returns the direction of the root segment of a curve. Root index returns the index of the root point of a curve. Next is the curve tip node. This node gives information about the tip of each curve. Tip selection returns a Boolean value of tip points. Tip position returns the position vector of each tip point. Tip direction returns the direction of the tip segment of a curve. Tip index returns the index of the tip in the curve. Next is the curve segment node. This gives information about the curve's segments. The segment length gives the length of each segment. Segment direction returns the direction vector corresponding to the direction of each segment. The neighbor index returns the index of the point from which the segment begins. Last is the hair attachment node. This node reads information about the attachment point on the surface mesh. It takes in surface geometry and its UV map as an input. The outputs include the attachment UV, which give the UV coordinates of the surface attachment. The surface normal gives the direction of the normal vector of the surface at the attachment point. The attachment is valid gives a Boolean value for whether the stored attachment UV coordinate is valid or not. The next section are called the utility hair nodes. The first of this section is the attach hair curves to surface node. This node allows you to attach hair curves to a mesh surface. The first few inputs of this node are similar to the inputs of the generate hair curves node, so I'm not going to delve into these because they do the same thing. The snap to surface checkbox snaps the root of each curve to the closest surface point. The sample attachment UV takes a sample of the UV map at the attachment point. The align to surface normals checkbox aligns the curve along the surface face normals. The blend along curve blends the deformation of the surface along each curve from the root. Next is the redistribute curve points node. This node redistributes control points evenly along each curve. The feature awareness checkbox reflects the underlying features of the surface in the hair system. The last node in this section is the restore curve segment length. This node restores the length of segments after deformation. This is done using data from previous states. Reference position is where you input the data of previous states. This is done using the capture and named attribute nodes. The factor parameter blends the overall effect. The pin at parameter pins each curve at certain point for the operation. The next section in hair nodes is the guide nodes. The first of this set is braid hair curves node. This node transforms existing hair into braids. How it does this is by taking in standard hair curve geometry as input and then defines certain guide curves from this pre-existing set of hair. The guide curves can be defined using three methods: guide index, guide distance, and guide mask. The guide index input specifies the center curve for each braid group using the index of that curve. If this is set, guide distance and guide mask are ignored. The guide distance defines the minimum distance between guides to create a new guide map. A guide mask determines which curves can be selected as guides. If an existing guide map exists from previous nodes, we can check the existing guide map checkbox to override all other guide controls in this node. The inputs below this are all used to customize the look of the braid. The flare settings adjust the shape of the braid's end. The hair tie settings add a hair tie at the end of the braid. Coming up, we got the clump hair curves node. This node clumps together existing hair curves using guide curves. All these inputs used for selecting guide maps are similar to the braid hair curves node, so I'm not going to go into this. Rest all inputs just control how the clumps will appear. Moving on, we got the create guide index map. This node is responsible for creating a new attribute called guide curve index that stores the index of the nearest guide curve for each hair curve. The node takes in curves and their guides as an input, and using guide distance, which specifies the minimum distance between two guides, creates a guide map. This guide map can be used by other nodes to have their hair follow the same guide structure. Last of this set is the curl hair curves node. This node deforms existing hair curves into curls using guide curves. All inputs and outputs are similar to the braid and hair clump nodes, so I'm just not gonna cover them. The last node we are gonna cover in hair nodes is a set hair curve profile node. This node sets the radius of hair curves according to a profile shape. The replace radius checkbox replaces the original radius with the defined profile shape. Radius sets the base radius and works only if replace radius is enabled. Factor min and max set the minimum and maximum values of radius. The shape defines the curve's profile.
Coming up next, we got the utility field nodes. Remember, one of the few nodes we tackled in the starting was the attribute statistic node. The major downside of that node is that it requires a geometry to function. And so in the new Blender 4.5 update, Blender added 3 new nodes to carry over statistical operations without needing to input a geometry. These nodes are the field min and max node, field variance node, and the field average node. Up next, we got the accumulate field node. This node is easier to understand on the spreadsheet, so I'm going to do that, the basic function of this node is to add the input field values based on the geometry's indices. Instead of outputting a single total value, it returns the current value at each element. It includes the option to accumulate values for only certain elements using the group ID input. Since it's a field, it supports multiple data types and allows for domain selection. It has three outputs: leading, which gives the running total of the values in the group starting from the first value; then trailing, which gives the running total in the group starting from 0; and total, which gives the total of all the values in the corresponding group. The next node in the list is the evaluate at index node. This node allows access to an element's attributes using its index. Which attribute to be accessed is given through the value input. The node offers several data types and has selection for domain. The last node in the list is the evaluate on domain node. This node basically allows you to switch the domain of the attribute you input into it. This basically allows you to access a separate domain outside the current field context.
The next set of nodes are called instance nodes. The first in the set is the instance on point node. This node basically allows you to instance an object or a collection of objects onto the points of another geometry. The node also offers you to pick instances which are to be used when your object or collection has multiple geometries that can be instanced. This is done using instance index. It is designed to be used with the collection info node. The node also offers you the options to control the rotation and the scale of the instances. The next node in the list is the instances to points node. This node basically takes in instance geometry as input and generates a point at the origin of the top level instances. The node offers a radius and position input to control the size and location of the points generated. Next in the list is the realize instances node. This node basically makes instances into real geometry data. It has a depth input which specifies the number of levels of nested instances to be realized. The realize all checkbox basically realizes all the levels of a nested instance into real geometry. Next in the list is rotate instance node. This node rotates the instances around a pivot point whose location can be specified. It has a local space checkbox which serves as a way to rotate the instance about its local space. Next in the list is scale instance node. This node scales selected instances around a center point which can be specified. It has a local space checkbox which serves as a way to scale the instance around its local space. Next in the list is translate instance node. This node basically translates the selected instances. Again, this also has a local space checkbox, which you know what it does at this point. Next in the list is set instance transform node. This basically combines the functionality of rotate, scale, and translate instance nodes into one single node, and it does this by using a transformation matrix. Next in the list is instance transform node. This node basically outputs the transformation matrix of each top level instance in a given geometry. The next two nodes are pretty similar in function, the instance rotation and instance scale node. These nodes basically output the rotation and the scale of the top level instances respectively. Now we're going to take on one of the most biggest and the most complex set of nodes called mesh nodes. The first node in this section is the edge angle node. This node calculates the angle in radians between two faces meeting at an edge. It has two modes of operation, signed angle and unsigned angle. In the signed angle mode, the node outputs the angle with a sign. Concave angles are positive and convex angles are negative. Flat and non-manifold edges have an angle of 0. In the unsigned angle mode, the node outputs the shortest angles in radians ranging from 0 to pi radians. Flat edges and manifold edges are 0, while edges fully folded back on themselves are pi. The next node is the edge neighbors node. This node outputs the number of faces sharing an edge. A value of 1 indicates a non-manifold boundary edge. A value of 0 indicates a loose edge not connected to any faces. Coming up, we got the edge vertices node. This node outputs the position and the index of the two vertices of each of the mesh's edges. Up next, we got edges to face groups node. This node clubs together certain faces into regions which are surrounded by selected boundary edges. Next up on the list is the face area node. This node outputs the surface area of each face of a mesh. Moving on, we got the face group boundaries node. This node finds the edges which lie on the boundaries of a specified region. The region of faces are specified by the group ID input. Coming up, we got the face neighbors node. This node outputs the vertex count and the face count of each face of a geometry. The vertex count is simply how many corners the face has, and the face count is simply how many faces have at least one common edge with the evaluated face. Up next on the list is the is face planar node. This node checks if all triangles of a quad or an n-gon lie on the same plane. It outputs a boolean indicating whether a face is planar or not. The threshold input defines the maximum allowable distance a point can deviate from the plane for the face to be still considered planar. Moving on, we got the isEdge_smooth node. This node outputs true for each edge of a mesh that is not marked as sharp. Up next on the list is the isFaceSmooth node. This node outputs a true value for each face of a mesh that is marked as smooth shaded. Moving to the meshed island node, this node provides information about disconnected regions of geometry, also called islands, within a single mesh object. The island index outputs the index of each vertex island. Island count outputs the total number of islands in the mesh. Coming up, we got the vertex neighbors node. This node outputs the vertex count, which is the number of vertices connected to this vertex with an edge. The face count gives the number of faces that contain the vertex. The next collection of nodes are called sample nodes. The first of this collection is the sample nearest surface node. This node retrieves attribute values of the closest point on the surface of a source mesh geometry from a sample position. It's similar to the geometry proximity node, but this provides the value of any attribute at the closest surface point, not just its position. The last node in this group is the sample UV surface node. This node finds an attribute on a mesh's surface at a specific UV location. The node basically finds the attribute on a location on the 3D surface that corresponds to a point in the UV space. It takes in standard geometry as input and the attribute to retrieve through the value field. The UV map input takes in the UV map of the object, and the sample UV input basically takes in coordinates to sample within the UV map.
The next few nodes we are going to cover are those nodes which I missed while recording initially, and the new nodes added to Blender 4.5 update. So let's go over them. The first node I'm going to cover is the string length node. This node outputs the length of a string you input in it, which basically means it'll count the number of characters present in the string. Up next, we got the find in string node. This node searches for a smaller string within a larger input string and outputs the number of times it found the smaller string and the position of the first match of the smaller string. Up next, we got the match string node. This node compares parts of two strings and gives a boolean result based on whether they match or not. You enter a string through the string input, and the key input is the string it is compared against. Up next is the format string node. This node basically allows you to dynamically change strings using Python style formatting or the Blender's format specifier syntax. This is basically proceduralizing text input in geometry nodes. That's the best way to put it. The next node we are going to look at is the instance bounds node. This node outputs the minimum and the maximum extent of all the top level instances in a geometry measured in 3D space. Up next, we got the camera info node. This node allows you to output the information about the selected camera object. It takes the active camera and outputs its internal parameters, which can be set in the camera tab. Up next, we got the bitmath node. This node basically allows you to do bitwise math directly in Blender. And this node comes with the standard bitwise operations that one must have in order to do such kind of math. Up next, we got the vector curves node. This node takes in a vector as input and maps its individual components to a curve. Up next, we got the mix node. The basic gimmick of this node is that it allows two inputs to blend with each other. But depending on the data type that you select it to be in, it has different functionalities. In the float data type, it takes in two float values and allows you to blend between these two float values using linear interpolation. It has a clamp factor input. Using the clamp factor checkbox limits the factor value between 0 and 1. If this option is unchecked, it extrapolates the value based on the two input values. In the color mode, the node offers an extra drop down to select the blending type. These include mix, darken, anything you might see in a photo editing software. Coming up next, we got the set shade smooth node. This node controls whether a mesh's face will appear smooth in the viewport and renders. It lets you choose whether to apply smooth shading to faces or edges and has a boolean checkbox to enable shade smoothing on selected pieces of geometry. Up next, we got the set mesh normal node. This node lets you assign custom normals to a mesh. It can store these custom normals in the form of three forms: sharpness, free, and tangent space. In sharpness mode, it gives you the option to remove previous normal data through the remove custom checkbox. You also get two boolean fields to define which edges or faces are sharp, letting you control the shading behavior with precision. In free and tangent space mode, it gives you the option to input custom normal fields to define the final look of the mesh. Up next, we got the smooth by angle node group. This node sets the sharpness of a mesh's edge based on the angle between its neighboring faces. Angle defines the maximum angle between the face normals that will be considered as smooth. Ignore sharpness checkbox smooths all edges even if they are all marked as sharp.
Up next, we got the named attribute node. This node is used to retrieve any attribute that is saved onto the geometry. All you have to do is type the name of the attribute in the text field, and that output is spit out through the attribute output. The node also gives the option to change the data type of the attribute the node gives out. Up next, we got the simulation zone. This node basically lets you change a geometry setup over time. Anything inside the zone gets iterated over every frame. It lets the result of one frame affect the next, creating a geometry setup that changes over time. And yeah, that concludes all the geometry nodes there are in Blender 4.5. It's fucking 3 a.m. I'm tired as fuck. Please, for the love of God, go to my Instagram and give me a follow or something. Consider subscribing. What do you mean consider? Just fucking subscribe already. Check out my ebooks. And yeah, it's been Radium. Stay curious, stay ethical, and once in a while inspect your tech.